Okay, welcome back to AP Statistics. This is Dr. Kling, still not affiliated with the College Board. And I want to continue the topic of scatter plots by talking more about the regression line. Okay, so let's say that I'd like to use an example here. And of course it's a made-up example since I make up everything in this class. So we're going to have two variables. The x variable is the amount of cigarettes per day that somebody smokes. Let's say is smoked over the last 5 years on average. And the y variable is going to be lung capacity. And I'm going to guess that the average is about 6 liters. I think I read that somewhere. And if it's wrong, so be it. I'm just making it up anyway. So let's say the first person we survey has averaged 5 cigarettes per day over the last 5 years and has a lung capacity of 6.1. The next person has averaged 20 a day and has a lung capacity of 5.2. The next person has had 0 per day, has a lung capacity of 6.7, and so on and so on and so on. So let's say we had dozens of people, and then we did a scatter plot, and we put lung capacity on the y-axis. Let's say 10 liters, 0. And then cigarettes per day on the x-axis, and I don't know what's the most anyone would smoke. 200 a day? That would be 10 packs a day or something, wouldn't that? That'd be pretty big. And then we just have a bunch of points that you can just put some random points. I assume it's kind of downward sloping, and I'll make it up as being linear. And then we have what we call a line of best fit. And we could just try to eyeball the data and draw a line through it, or we could try to do an actual mathematical line, and I'll show how to do a mathematical line momentarily. But I want to introduce the important jargon. The line... Okay, you may have seen the point slope formula. Remember point slope? That's y equals mx plus b. Alright, well, kind of forget that because we use y equals a plus bx. So now we've got b acting as the slope, and the constant term is a. So we're kind of doing that. So it's y equals a plus bx. So a is the intercept and b is the slope. So in the context of this problem, the b measures the change in lung capacity for each additional cigarette per day. I'm not promising I've spelled cigarette right, doesn't look right, but whatever it is. And so presumably B is negative, that is, the more cigarettes you smoke, the lower the lung capacity. And A estimates what happens when x is 0. And that's sometimes meaningful and sometimes not. For example, if you had something where the x variable was height, like the average height of a man, then you wouldn't really have a reasonable interpretation of what would happen if a man's height fell literally down to 0 because we don't observe that. So sometimes A is interesting and sometimes it's not. In this case, it probably is interesting. It estimates what the lung, in this case, it gives you average lung capacity for non-smokers. So in this case, it gives you something interesting. It doesn't always. Okay, so that's the equation of the line of best fit. And actually what I'd distinguish three variables. There's x, y, and what I call y hat. So x is the actual variable. Let's say 10 cigarettes per day for the first person that we have in our sample, or one of the people in our sample. Y, let's say 5.2 liters of lung capacity. And then y hat, suppose our equation was 6.4 minus 0.1 x. That is, if y hat equals a plus bx, a equals 6.4, b equals negative 0.1. If that were true, then the y hat for x equals 10 would be y hat is equal to a plus bx is equal to 6.4 minus 0.1 times 10 is equal to 5.4. So in that case, y hat would be 5.4. And then I'm going to have something that I call the residual, E, and that I'll define as, it's right here, E equals y minus y hat, or 5.2 minus 5.4 is negative 0.2. What that would mean graphically, let's see if I could find a point that looks sort of like that. It would mean that the point lies below the line. So the residual is the distance y minus y hat, point minus the line, and in this case it's less than 0. In this case here, it's greater than 0. So this one is a positive residual, greater than 0. This one's a negative residual, less than 0. And if you fit the line correctly, on average, the residuals will equal 0. So if we do this for another set of x's and y's, another, and we just keep going, we add them all up, the sum of the residuals, adding them all up, will be 0 if we've properly come up with the line of best fit. So that another way of saying that is that the residuals balance each other out. There's just as much error on the positive side as on the negative side. So the points are just as far above the line up here as below the line down here. That's the notion of adding the residuals, having the residuals sum to 0. Alright, so what we call the line of best fit is the one that minimizes the sum of the squared residuals. Okay, so even though on average they're 0, there are some positive and negative values, and we're trying to have, in some sense, the lowest absolute value of residuals possible. That's what, if we keep moving the line, twisting it around and moving it up and down to sort of minimize the absolute value of the distance from the points to the line, the absolute value of the residuals. Well, the absolute value is a hard thing to work with, but the square does the same thing. So working with the square and minimizing the sum of squared residuals will help is the typical approach for getting a line of best fit. And let me give you what that formula. So that gives you formulas for A and B. For A, that's the easy one. So the intercept will be equal to y bar minus b x bar, where y bar is the average of all your y's. So in this case it would be the average of everybody's lung capacity. And then minus b x bar, and x bar is the average of the x's. So that would be the average of everybody's cigarette smoking in terms of cigarettes per day. And so whatever the slope we get, the intercept will be the average of the y's minus b x bar. Okay, so that's pretty easy. But what about b? How are we going to get b? Well, b, I won't prove it. It involves actually a little bit of tricky calculus to prove it, because we're trying to minimize this this sum of squareds. We're trying to minimize, in some sense, y minus y hat, the sum of those squared, and y minus y hat, we can write that as the sum of y for, let me put some indexes in there. Let's put y hat I. So that means each observation is numbered 1, 2, 3, 4, 5, so on. You don't have to worry about this, by the way. I'm just doing it to show I can do it. So substitute for y hat, a plus bx. You get this, square it, and that's the thing you're minimizing. The solution for A is this, and the solution for B is this kind of ugly thing. yi minus y bar times xi minus x bar over sum of the xi minus x bar squared. Again, don't really have to know this. In some sense, this is the covariance of x and y over the variance of x. If that'll help you think about it, fine. If not, it turns out it doesn't really matter a whole lot. Let me introduce another piece of jargon called R, which is the correlation coefficient. And that's defined as, I think it's something like this. I hope it's something like this. Okay, so it's an ugly thing. I usually write it as sigma xy over sigma x sigma y. And so this is a covariance term. It's the same thing that we had up there for B. Covariance term, and these are the standard deviation of x, standard deviation of y. So this is the one that this is useful, and B, you can see the relationship between B and R. That is sort of B is equal to, maybe I shouldn't put sigma. I'm going to change those to Sxy over Sx Sy. Using S instead of sigma indicates I'm doing it with sample data as opposed to theoretical data. Okay, so let's let B is equal to sxy over s squared x. R is equal to sxy over sxsy. Now we can do some algebra to solve for r in terms of b. That is, r is equal to, let's put b in there, sxy over s squared x times sx over sy, and that'll give us sxy over sx sy. Is that right? Absolutely not. That's not what I want to do. Okay, so we want b is equal to sxy over s squared x. That's what we're trying to get. Is equal to r, which is sxy over sxsy times sy over sx is equal to r sy over sx. And that's something that shows up in a fair amount of problems that we, at least that we have in the textbook. So that's another formula for b. So what that means is if we were given x bar, y bar, sx, sy, so the mean of x, mean of y, sample standard deviation of x, sample standard deviation of y, and the covariance and the correlation coefficient. If somebody just handed us the correlation coefficient r on a silver platter, we could then find a and b. So in our hypothetical example, suppose that for the cigarettes x bar, let's say, is 28 per day, sx equals 8. For the lung capacity, let's say it's the average of 6, sy equals 0.7. I have no idea what it is. And let's say that the correlation is negative 0.3. Okay, so that there's a negative relationship between cigarette smoking and lung capacity. Now we could find a and b. b is equal to rsy over sx is equal to negative 0.3 times 0.7 all over 8 is equal to negative 0.21 over 8 is equal to negative 0.026 or something like that. So that's b, and then a is equal to y bar minus b x bar is equal to 6.0 is y bar, and minus b means a minus 0.026 times x bar was 28. So whatever that turns out to be, that looks kind of ugly. Hang on. Something like 0.74 about? Oh, 6.74. Remember, we're adding because we're subtracting a negative, so that would be our a. So our final equation might look like this. Y hat, predicted value for lung capacity, is equal to 6.74, that's our a, minus 0.026x, where x is number of cigarettes per day. So that's a whole bunch of stuff about the regression line, and I think I'll stop there.